Okay, so this last little leg is basically going to try to just kind of get a bit of information out in terms of how we go about with nonlinear outcome or nonlinear estimators and panels. This one, remember that we were looking at previously at the conditional Logit, or basically the Probit and Logit models in the conditional Logit. And then I was just going to show that basically we can use these same techniques in this using the correlated random effects model. Remember, the only thing we're doing here is instead of actually including something that's trying to control for the CI, now I'm adding A to it. Let's hold the conversation for another day. For the CI, let's leave off the A. In this case, and basically instead of trying to use a dummy variable method sort of for that, we're just going to try to model it by creating something that is akin to a structure that's trying to approximate the CI term. Okay, same procedure, same methodology that we used in the linear models before. Okay, now if you wanted to, you could go to the website. This is just a very basic version of his. He went into a lot more detail than what I'm going here, doing a simulation in this case. The only thing I wanted to show you is basically from simulated data what would happen in terms of the IPP problem. Remember, it's we're not consistent in terms of our estimates of the unobserved effects, which is basically leading to not being consistent in terms of the variables of interest. So in this case, the regression results, the true value is 1. That's the way I simulated it. If we were looking at just a plain Logit model, that basically we would say the unobserved effect isn't problematic for us whatsoever, so I'm just going to use the treatment variable and not consider anything else. You could see that basically we would have an upward bias in terms of our estimates. This is supposed to be 1, and basically we're at 2.09. In terms of a Logit model with dummy variables, just assuming that they do a good job and they don't cause IPP problem, you can see that it does at least come down a little bit and closer to 1. But in some ways, we know that there's some issues here. There is one command that you could use. It's called the BIFE. Basically, I think it stands for bivariate fixed effects model. And what it does is it estimates the model, just like the one here with the Logit and dummy variables. But then in the procedures of the calculation, it actually does an analytical correction. It tries to adjust for the bias. Okay? And you could also ask it to do, if I remember right, you could also ask it to do a split panel, split jackknife correction, or the analytical. But you can see that it does a really good job as well. Right? So we've brought it down to basically about 12% over our true value. And then we could try the C-Logit model. Remember the one I said we condition on the unobserved, but we don't actually estimate it. And we should get a consistent estimate in that. And again, it's not too bad, right? It's done a pretty good job. The problem here is that what if we actually need the propensity scores for something? What if we need the marginal effects for something? Okay? Remember, we can't just use these estimates because we need to go through and calculate more to be able to get our marginal effects. In that case, here we might be okay because in this case we're using the dummy variable model approach and we've just made a simple correction. Here we didn't actually estimate them, so I'm not so sure. I would need to check myself on this whether you can get marginal effects out of it because I just don't use the command very much. Okay? But also notice that in that correction, there was an observational adjustment. Okay, so there are some things there are some adjustments or things we have to deal with in this case. We have to figure out why it dropped 295 observations. Okay, there are particular reasons for doing this, especially when it comes to basically we drop some observations because of helps with improvement of the overall convergence of the model sometimes. So my guess is that's probably what's going on here. Okay, but we see that we can estimate these models, and in some ways it's not always bad to try to use the dummy variable model in this case, because it didn't do a poor job, but it can do a very poor job depending on the properties of the data set itself. I could have tweaked how the relationship was between the CI term and the other right-hand side variable. I could have made it more noisy. There's all kinds of things that could go on here, okay? And that's the things we have to keep track of. If I went and actually added the CRE approach, it did a pretty good job overall, okay? It's only 3% or 4%. So there's always a possibility, and it's not always the case that it's always going to be better too. I could have, like I said, adjusted the properties of this data, and these would have done very poorly, and for some reason this one would do well. Okay? But the thing is, that's why we have to know the data, the variables we're using, and we have to make our arguments that they meet certain properties. Okay? So if I was to ask you to do a practical for this, I won't. We'll kind of go through it. Basically, what we could do is we could try estimating a pooled Logit model that does not consider individual heterogeneity, just like we did before. And we can calculate the average marginal, or basically we want to consider estimating the average marginal effect for experience and merit. Then we could estimate a model equivalent to a pooled Logit that includes the binary variable for each ID. This is what I mean by a dummy variable. Basically, I use the factor on the ID so that it includes all the specific dummy variables. And in that case, you could do the method we did before. You could just basically type in GLM, left-hand side variable, our other variables, and then factor ID. But there's a better package for this called Fixit. Basically, it's a high-dimensional fixed effects way of doing GLM models. Okay? And we would use the FEGLM and basically calculate the average marginal effect for experience and merit again. So remember, when I do this, as long as they're calculated, as long as our dummy variables are calculated, we can calculate a marginal effect. But whether we're getting bias in there, we're not so sure, right? If it is it can be problematic. Then we could also estimate the conditional Logit model, and in that case, we would, couldn't really do the marginal effects, and then we could estimate the CRE model. I'm trying to remember if I put it on the next slide or not. Okay, yeah. So if I was to do this, did I even tell you what? Apparently, I was getting a little lazy here. I didn't even tell you what data set to use or anything. Apparently, I'm not doing my homework. Oh, I put it in the title. Okay. I still consider myself being a little lazy, but... Okay, so, let me go back. Come on. Okay, so we're using, no, that can't be, is it Woolridge? Let me see if, I'm not sure if that is Wooldridge. Yeah, see, I told you I was getting lazy. It's not Wooldridge. It's under the PGLM package for union wage. Okay, so in this case, we're basically going to be looking at union are you part of a union based on your experience, health, log wages, married, rule. I was simplifying by I could have done some groupings within the school, but I just told it to factor. Actually, I'm not sure if, yeah, it is actually going from a min of 3 all the way to 16, so it might have been actually better to group these in some way, less than high school, and so forth. Factoring for the year dummies, and then I ask it to do the Logit. Okay? In this case, this is like the standard Logit that we did before. This is what I meant by we're just assuming that the unobserved effects are not really meaningful to us, so I don't attempt to control them. We usually refer to this as like a pooled Logit. Okay? In terms of the next sets, I can actually use the C-Logit outcome, and from that, I think that's coming from the PGLM package. And all I have to do is state the same stuff, but this time I have to tell it strata is equal to, or is the ID. Basically, that's just telling the data set, or telling the program, this is what the CI, the unit of observation is. Okay? And in that sense, once I tell it that, I can run a C-Logit. Again, it's not going to estimate it. It's only going to condition on it. Did you have a question?
Yes, yeah. Regarding this question, say I'm dealing with the common mechanism with what I'm doing. Can I say maybe I have more than one structures? That means how can I incorporate maybe one?
So strata here is like if I included it's like factor for ID. Strata in the code is meaning, this is what is our unit of identification. It's not meant to be the strata that I think you're referring to. Yeah, it's not that strata. Or maybe in this command that's what it's meant to be, but in this case it's almost like using, it's identifying, it's not just a factor, it's the unit of identification. Okay. And in that case, it would run the C-Logit. And then this would be, so the reason why I was telling you the FIXEST package is because you can use something called FEGLM. If I ran this without that, if I just ran the GLM and I told it to factor on the ID, it would be running for a few minutes. It's one of those times where, remember, every time when you're adding these particular additional covariates, especially MLE models, what's going on is you're increasing the amount of the estimation time by a lot. Okay, it doesn't handle that outcome very much. But the FEGLM has a little trick that allows it to estimate these models very quickly. Okay, but it's doing exactly the same thing. It's basically creating a way of creating an ID for each of the individual, or a dummy variable for each of the units of identification. Okay, so that's one way of running this, and I would advise that if you're going to do that type of method. And then we could also, again, do the CRE method. Okay, basically create averages for all the time-varying variables, and then we can basically include those in our model. It would probably be helpful for me to check whether these are varying, because I don't actually do that. I'm just assuming very quickly. But in this case, it should be fine. And then, nothing really changes from this, and basically it's just changing the package. So for the conditional logit, we have the clogit command. For the logit with the dummy variables, we use the feglm command. And then we have our CRE version of this. We just have to construct the means for the time-varying variables. Once we do that, hopefully this runs, if everything else runs. Hold on a second. Let me try to get in a better format. Okay, let me do... Sorry, I thought I already had these downloaded. Let me see how long it's going to take. Yeah, there we go. Okay, so this is just a simple version of the table because I couldn't get it to come out in the other one. Go up. There we go. So in terms of the pooled logit, depends on what our variable of interest is here, but let's say it's log wage for right now. You can see that with the pooled logit, I'm getting an estimate of 1.48. In terms of the conditional logit, which should be consistent, is 0.730. Dummy variable model with, I didn't use the BIFE, so there's no analytical correction here. But if I was to use that, most likely this might come down, given what I found here. And then in terms of the CRE model, it's so some of these three, they're a little bit, not exactly the same, but there is some, consistency across those three measures. So you can see that basically, even though we don't have exactly the same methods we can use with linear models, we do have methods that allow us to, in some ways, possibly mitigate those problems when it comes to the CI, the unobserved or unit-specific effects. Okay, but this is why I'm showing this is because these same methods, even though I'm using them here, I could use some of them I could use with Probits. Other than that, you're going to get into a world where you might not be able to use something that has a method of conditioning on the CI term. So you might have to use something else. Because there's not a huge, one-size-fits-all version of this. Okay? This is only 4 logits. Imagine doing it across all the different models that are nonlinear. Okay? So these are just sort of give you an example of what's possible. Or what's possible in terms of a headache later on if you're using these methods. Okay, so that is roughly the panel sort of context of these nonlinear models. What we're going to look at next is it's related, but not, you know, not as straightforward, I guess. It's just I would want to talk about it a little bit because some of the outcomes that you are, or the model strategies that you are using are not sometimes, they're observational, but they're almost like you're trying to maybe set up an experiment in a sense of maybe doing a survey or something else that you're trying to condition on some type of policy, and you're trying to think about designs that allow you to hopefully maybe claim causality. Okay? So that's, it seems like an awkward, you know, branch to what we're about to do, but it's sort of related. Yeah. So in terms of what we've been doing so far, most applied econometricians, our focus, or the headache that we always face, is trying to uncover a causal effect, or at least something that we hope is close to a causal effect. That is a model estimating how a variable, the treatment, impacts an outcome. Basically isolating the effect of the treatment while ruling or addressing or ruling out potential confounding factors. So the key challenge to most of this is basically we only observe one outcome of two. I'm not sure if you really think about it too much, but whenever you're claiming that effect and everything, you're actually assuming a world where you actually think that you saw both outcomes. You know, there's two possible outcomes, and we're saying the same person would choose we're comparing those results in some ways. And in that case, that's where we get into a little bit of an issue that we need to be careful in how we're describing this. So basically, we observe one outcome, yet there are two potential outcomes. One if exposed to the treatment, and one if not. So this is the central counterfactual problem. What would have happened in the absence of treatment? Okay? This is where we get into those techniques that everybody likes to use, but they're some of the assumptions that go into them are a little bit more difficult to support. Okay? So research design usually, in a nice world, would be something like a random controlled trials. Basically, treatment is randomly assigned to units, ensuring that both the observed and the unobserved characteristics are balanced across the treatment and control group. We like balance between the two because then it is like a world where we have ability to say something about, you know, the two choices and the one choice we see, but because we have a balance type between the treatment and control, we can actually say or be close to thinking about it as causal. Okay? The other that everybody likes to do, I know everybody's always interested in these types of models, is referred to as difference in difference. Okay? And these are very nice, and they're very nice studies when they do it, but they're also very hard studies to do. So the problem, though, that we have is that a difference in difference is on observational data, and it's more of a quasi-experimental outcome. Okay? We'll kind of get more details with that. So the quasi-experimental method is used when randomization isn't really feasible. So think about it as it's not randomization in the most common sense that you would think of, but we can leverage the fact that we see differences across groups and differences across time, and then if we take those two differences and difference them, then we get what's referred to as a difference in difference effects. Okay? And in that case, it should approximate what the counterfactual might have been. So both approaches aim to approximate the counterfactual. Basically, what's the effect in the absence of treatment? So the effect that I am viewing is the effect of the treatment. So both approaches, like I said, approximate the counterfactual, which is necessary for hopefully credible causal inference from what we're looking at. From, I say policy here, but there's a lot of different things other than policy that we look at for this. Okay? Now, the reason why these fall into the panel side of this, or what we're doing, is because basically we typically need information across time. Once people are treated or receive treatment, we need to see how that's changing over time a little bit. Usually there's some portion where they're not treated, and then the treatment comes in, and then we'll see it after that effect. That's why it falls into the panel side. So in terms of the RCTs, basically the design is supposed to be a treatment is randomly assigned to units such as individual schools, and then we're trying to use, which in expectation, basically we're trying to balance both the observed and the unobserved factors between those two groups. And then basically I've already said this sort of, the outcome differences between these groups are attributed to the treatment. Okay? The approach is still for observational data. Sometimes this is only one version of this, but the reason I'm bringing this up is because sometimes, even though we've done the best we can with the RCTs, there are things within the model that sort of still make it act like it's not random. Okay, there's choices that are made that we still can see that maybe cause issues. So sometimes the randomization isn't completely possible, and we have to use another method that might help us out. Now, the one I'm doing here is only one of 5 that I know of that I could have shown an example of. Basically, it's like a reweighting strategy that we can use to try to take something that is observational, maybe not perfectly random, and hopefully make it random. Okay? In this case, we're just going to use the IPW basically to reweight individuals by the inverse probability of receiving treatment. Okay? The way to say that is basically we estimate some type of Logit, or in my case, the example I'm going to give is using the LPM, because I said it does a decent job. Then using that to weight any type of outcomes that come out in the model. So I'm basically going to weight the treatment effects, or the average treatment effects, by those probabilities. You know, so that it's just basically trying to, in some ways, hopefully making the treated and the control groups more comparable if the treatment is not random. Okay? So when we use these propensity scores, it's basically stuff we've done before. We could use the Logit, we could use the LPM, and in that case we estimate the model and predict the propensity scores, and we use that information so that basically these are the determinants, so, but we're just basically trying to predict the propensity score. So we take those, so the probability of not being treated is given 1 minus the propensity. And then basically those that did receive the treatment would be over the propensity. And then basically sometimes we'll keep both the determinants for the Logit or the binary model and the model that we run after in the RCT the same, but that's not always the case. So keep in mind that some things that predict the probability of being treated are not the same as determine whether on the dependent variable, you know, of the original outcome. There's differences there. There's how it's basically thinking about, you know, well, no, I won't go into that. But just note that the z and say the x that we use in the regular model do not have to be exactly the same. There can be differences determining the propensity and the outcome. So in terms of the average treatment effect, we could basically model it as we typically do, but basically we're just going to divide through by the propensity on those that whenever they have y, we're basically weighting the outcome in terms of the propensity score for when you are treated and not treated. And then conditioning on the z, we could basically pull this out in terms of the expectation of y1 given the z's. So in this case, this is just one version. We could also think about flipping it in terms of those of the untreated as well. But again, this is sort of that stuff that we can show, but it doesn't make a lot of sense. It might be better to think about it in terms of just running the models. All we're doing is taking the models we've run and then basically weighting them by those propensity scores to get new answers. Okay, think about it that way. And there's a lot of different versions or extensions of this. This is considered the simplest version. Okay, these are just 3 of the ones that I picked out of many. So when you're trying to do this thing, each of them have their own properties that are nice. And some of them are just trying to improve on other assumptions or reduce the amount of burden in terms of assumptions for, say, certain methods. So like the doubly robust method is combining IPW with something called a regression adjustment. Okay? In that case, it's just sort of a reweighting strategy. Maybe that's the best way to think about it. If we know something's not random when we're actually creating these average treatment effects, what if we were able to reweight the model to make it something that wasn't random and make it seem random and then recalculate? So it's like just reweighting. It might be a better way of thinking about it. Okay? And then these are other approaches that have been used before as well. So the example I wanted to give you comes from a paper, which the citation didn't really work right, Finkelstein et al. 2012. So basically, to give you an outline of what's going on here, basically we have a group of uninsured low-income adults in Oregon who are selected by a lottery to given a chance to apply to Medicaid, sort of a state public health insurance that basically just will supplement the insurance that you already have to improve, well, it's meant for it's supposed to help out low-income adults, and you know, whenever they become financially constrained due to health outcome, due to their health. Okay, and it's through a lottery system, so that should be random, right? You know, if we're doing a lottery system, those chosen should be random. Okay, in this case, we can basically go through a lot of these things, but basically we're focused on this out-of-pocket medical expenditures. We want to know whether this lottery system hopefully helped out in terms of those out-of-pocket expenses, or what the effect was. So what I did was basically take a stated version of this particular method and data and converted it in R. So out-of-pocket expenditures, I guess is the name. It's continuous. Basically, we're just thinking about this is how much you're paying out of pocket, not covered by insurance. Okay? And then we have, over in the last 6 months too, and then we have basically the DOWI, I guess, is the treatment. So basically, you win or you are selected into the lottery of this particular Medicaid type program. Okay? The state is supposed to have randomized individuals for this. But what sort of happened was, whenever you were chosen, everyone in the household became eligible. So what happened was larger households were more likely to be treated. Even though it was meant to be random, there was a little bit of a complication, because it wasn't just that you were being picked, you could then join. It's that I was picked and everybody in my family could join. So there was an issue there. So basically that was what was going on. So meant to be random, meant to be an RCT, but then all of a sudden possible, not so random. Okay? So, yeah. So a lottery type system is meant to be, it's like a lottery. Basically, think about a lottery that you go and pick random numbers and then your numbers are drawn and you win. It's not that simple, but think about it as, if I remember right, the way the lottery system was working, they were using information about individuals, which usually is contained in government information. And then it's like a lottery system that you would have for, say, a draft. You know, there's a certain people that are chosen within the system, and it should be random from that. So it's not, that's the way it was supposed to work. Whether it was completely all the little bits and pieces, I'm not so sure about. That answer, I'm not sure. Yeah. Okay. So let me just make sure I got all this. Trying to make sure I'm not missing anything important in there. Okay, yeah, so that's the general sort of gist of what was going on. Whoops. So in terms of the lottery system itself, in terms of out-of-pocket expenditures, basically, I'm missing something. Hold on. Where am I? Hold on. Okay, I'm missing one of my variables for some reason. In this case, it should have been either that or my. Yeah, so it should have been exactly 49.7 of the lottery participants were selected. And it looks like either I missed a variable or I messed up something. Give me 1 second. Just want to see something. Variable should be in there. Okay, I might have to check it again, but something seems off to me. Sorry. So there should be something in there that basically says the 49.7% of lottery participants were selected to be NR treated for our outcome. That measure should have been here, but something, like I said, something feels off on that, so I might have chose the wrong variable when I was doing it. And then the problem also in this case was that 28.1% of those enrolled. See, this is where the weird part. This should have been 49, and this one should be 28, but it added a 1 to it. I'm not sure why. That's why I think something's off there. But eventually I enrolled in the Medicaid. So there was a sort of, we could analyze it a little bit separately because there was a problem with that as well, but I'm not doing that here. Okay, so if I run this as an LPM model, I didn't really care about the Logit Probit stuff right now, so I'm just going to run the LPM. On the lottery variable by itself, so if I don't run anything other than any other covariates, then the effect that I found is a reduction in terms of out-of-pocket expenses, which is what we want. We want this to be something that reduces how much comes out of my pocket. Okay, it reduced it by 49.66 or $44.66. In terms of even when I added more and more controls about demographics, specific characteristics about the individual, it still only ranged between $45 to $40 in terms of reduction. So that's fine. But remember what I said, that basically in this case, more people were, or larger households were actually being sort of, it was causing an imbalance. So what happened was we need to think about trying to reweight this before actually going about calculating the average treatment effect. Now, if I was using Logit, I would have to go through all the marginal effect. Because I was cheating and using LPM, basically I can just look at the coefficient. So in that case, but so if we did want to reweight this by the inverse probability measure, and I'm going to reweight, sorry, the one I'm going to reweight is, make sure I'm doing the right one here. I want to reweight this one because in the actual paper they actually show that this one probably is the most likely, has the most likely the proper controls. If you want to go through the paper you could, but this is the one I'm going to choose. If I actually wanted to try to reweight this, then I could basically bootstrap that particular outcome to see how much it might actually adjust in terms of bias, in terms of my outcomes. And then I look at it in terms of weighting and see that basically by reweighting, it doesn't really change my result too much. So we're not expecting a huge difference if the RCT was probably run correctly, or at least whatever we're seeing that's causing the imbalance isn't too much of an issue. But I can tell you in some cases when I've seen these things and I've seen some reweighting that I've seen some huge adjustments. Okay? That can give you an idea of how well the RCT was set up to begin with. Okay? So in this case, I would say that it didn't do a bad job, even if there's oversampling in terms of larger households, or winning in this case. Overall, it didn't cause much of an issue. We're still roughly in that same ballpark range. Okay? So what I'm trying to show this to you is basically there are a lot of reweighting type strategies, but it's not guaranteed that they're going to make a huge difference in your outcome, especially if your overall method is, or your setup is very good. Okay? Ooh. Yeah. So that's an RCT. I kind of do that just because usually when Steve is here, he kind of does those things to discuss them, because there are a lot of people using RCTs. Okay? And this is a big field. The one that I typically focus on, and is not saying it's better or worse, but it's more likely that you might use something more like this, which is a difference in difference method. Okay? So in terms of natural experiments, we typically focus on a difference in difference because it's very popular, in the sense that we think that we're actually scientists, that we have a control group, we have our treated group, and we're more like we think of more of it like a lab. We think about it being a little bit more in the scientific method. So a lot of students, they typically start liking to do this. They think it's a very neat experiment, very good, very interesting. And the thing is, we're trying to mimic a scientific experiment by comparing a pre and post treatment. Okay? Post treatment being that basically we have a time frame after some type of new policy or something comes into effect, and we see a difference between those who received the policy or treatment and those who did not. Okay? So we're going to have both groups prior to the policy, and then we're going to see everybody, or hopefully everybody, after the policy, and any difference associated between the two groups should be, in cases where we've done a good job, the effect of that policy. Okay? So examples of natural experiments can include things such as, in terms of North and South Korea, separation during the war, East and West Germany, even even in Africa where they've done studies here where they've actually used differences between, so they have maps that they've tried to create ethnic boundaries prior to colonialism. Then those ethnic boundaries, when you had the colonial come in, they had their own boundaries that went on top. Some of those colonial boundaries split ethnic boundaries right down the middle. So you had ones that were going to be subject to certain rules of the states, and other in the same ethnic group that's maybe separated due to being French versus English colonies. Okay? So that's going to be two different systems on people that should be very similar. Okay? So that's one way they've done those systems here.
Yeah. So will this be done mainly on the spatial data?
No, you can do it, well, it's not exactly always spatial data. So they've done this in terms of, it's about defining the groups. That's the biggest thing. So spatial helps with that because once a border comes in for whatever, then up to coming, say, from the east and you get to that border, there's a certain rules that are followed or certain guidelines that are followed on that side. Once you go over the border, certain guidelines are followed on the other side. So spatial typically does help with that.
But thinking about that, if you're looking at data like municipality data, you and stuff like that, where after some time they change the words are now no longer, you are no longer in what, you are changed your next space.
So you have to have consistent measurement within the space. That's the problem too. So in that case, if you're sitting there switching around the boundaries all the time, it has to be well set within the time frame that you're looking at. There might be methods to deal with that switching, but I'm not as familiar with that. So, but the thing is, there is a huge expansion in this literature trying to deal with problems like that. We're trying to deal with unobserved heterogeneity. We're trying to deal with the fact that groups might, over time, learn that the treatment is good, so they want to try to figure out how to get into it. They change their characteristics, which then mess our experiment up. You know, there's things that we have to figure out how we might be able to deal with. So the ones I'm talking about here are the basic. But just like I was talking about with the quantile literature, the literature in terms of difference in difference is expanding as well. That I'm not as familiar with, so I'm not sure. I'd have to have more details of what you're talking about, probably. Just, are you talking about their borders are changing, or what was it? Okay, so that I've dealt with some of that before with if you're trying to define specifically who was in control of what. Like whenever we were doing some analysis in Cameroon, there's portions that, or a large portion that was French versus smaller portions that were British. That's problematic. But I wouldn't be surprised if somebody's come up with a way of actually trying to deal with those issues. Sorry, somehow I cut myself. Okay, there we go. I have everything in my bag. My wife has joked it's my purse, so I have a lot of things in there. Okay, so in this case, so I mean, but see, the reason I was bringing that up is there's been a lot of research and a lot of newer information coming out in historical documents around in these universities. Stellenbosch and UCT are putting out a lot of their information that helps you define groups, go about defining information at a time when you were better able to separate out groups in terms of identification. Now, not so much because now there's a lot of freedom of movement in terms of we'd have overlapping systems. So there's a lot of things, but those original documents can help try to figure out ways of creating similar methods to this. But again, it's something you have to kind of go through in terms of what type of data they are releasing.
For difference, right, this technique, is it popular within the time series space?
No, it would have to be a panel in this case. You got to be able to follow the group. So there's a group dimension that you can follow, and we got to assume that there's no switching. There's nobody being able to move around, and there's a time dimension. Those are sort of set. Without the group dimension, it's not a difference in difference anymore. Because the only thing that helps us out with this is the fact that we can difference over the group, then we can difference over the time, and then we take the difference between those two things. That's where the thing is. So if it's only a one dimension, it really doesn't help us. But again, my knowledge of time series or those specific aspects are a little bit low, so you might want to check to make sure I'm right. I just can't think of one that doesn't involve a group type system. Okay. So we're always focused on, we're trying to follow the same individuals that are observed over time, and we want to be able to classify them. Either you're treated or you're not. Control group, treatment group. In this case, if we're doing a basic model, basically post in this case means, in the simplest terms, we have a time before treatment and we have a time after treatment. That means the treatment is happening somewhere in the middle. Okay? So anytime we're looking at the post, we're thinking that post is being equal to 1 here and post be equal to 0 here. So it's a binary variable, either after or before. In terms of the treated, we have two groups that we're focused on. The treated receive a 1. The control equal to 0. So basically it's identification of the treatment, of receiving treatment. Yeah.
And I was just trying to rehash again. So the comparison is between the treatment and is the control group.
Yeah. Yeah, so we only view the treatment and the control for now. And the simplest, what we call the 2x2 model. This is the simplest of the cases. Okay? So basically there's some assumptions that go on to here that basically once I find out that I'm in the control group and I don't like that and I want to be in the treated group, I try to cheat and get myself in the treated group. Or once I know the difference between the treated and the control, I start changing my behavior for whatever reason. I change my behavior in the treated or I change my behavior in the control. Okay? So we're trying to make sure that once you're basically in a group, I don't want to say you're stuck there, but that's what it is. So basically there's no spillover effects. Treatment does not affect the control group. Or not being in the treatment, the control group doesn't affect being treated. No anticipation. I can't know that something's coming and decide to shift over to the other group.
Just trying to check, so the treatment can be like a shock?
It can, but right now I'm trying to treat it more as a policy. But that's why when I brought up the things before with that I've seen some, these are old studies, but some people have looked at, things that all of a sudden overnight a new boundary was created and now people are separated out from where they were before. One of those being like North and South Korea. Once that wall went up, You were on your side, I was on my side. And then basically you can see the overall difference in the societies over time. Because the people were exactly the same. Same language, same customs, everything. It's just which side were you on whenever the wall was built. So it's in some ways, it can be that could be considered a shock. But for right now, I'm thinking about it more as a policy. So thinking about, if everybody in this room and I created a policy to where, I decided all of a sudden the line is here. And I started being able to split myself off, and basically we sat over here and just all stared at each other versus over here where I kept teaching. And there's a wall here and you can't come over to this side, and then we try to do a test at the end. And thinking about, all of a sudden it was there, and I've treated both groups differently. I mean, that's a really weird example, I know, but it's just trying to give you an idea that basically it's suddenly there. There's no anticipation. I didn't give any warning, and then all of a sudden the policy's there. And in some ways, this group should be not completely homogeneous. There's some characteristics I should be able to pick out, but overall you have the same, hopefully similar goals going forward. Okay, so there's a lot of things you could do in this. But these are some of the things that we have to consider. There's no spillover effects, no anticipation. And parallel trends just basically says, given everything that I can see across characteristics, who you are, things I can control for, if I can control for all that, and everybody after those controls is moving in a very similar direction for whatever the outcome was, then once the treatment is there, the only difference between the groups now is the treatment, because everybody was in what we refer to as a parallel trend. Okay? Like I said, this is the simplest of the versions that we have. Actually, this isn't the very simplest, because the simplest is basically no controls. If I didn't have that, that'd be the 2 by 2 as we call it. When we have controls, it's meant to be, those controls are meant to sort of get the little specifics about you that I can't see that are not related to the treated, or to that outcomes that might make you be out of the parallel trend. Okay, so this is a very crude way of kind of thinking about this. Okay, we're thinking about the blue as being the control, the red as being the treated. Now, before the two, in each kind of treatment, so basically T0 and T1 here, we think about the treatment as happening somewhere in the middle. And before, they're both going along fine. We've sort of balanced out everything about the people. And what happens is once we reach where the treatment comes in, there's a vertical jump. Once we have that vertical jump, then they continue on their path. Now, there's a little problem with the way I drew this, because I was having little issues whenever it wasn't doing what I wanted to. Really, the way this should have done is it should have gone this way, bounced up, and then continued on a parallel trend. So this one actually should be down a little bit. But what we see in life, because remember, this treatment is happening in between. It's like, one day I'm here. Then at night, this treatment happens, and then I come back the next day, and I measure my outcome. So I have a measurement here on the first day. Treatment happens. The second day, I have a new measurement. Now, if I'm only concerned about the measurement, the difference, you would assume the effect is this. Well, that's not true. The effect would actually be when it came in, and then the parallel, which is what it's supposed to be going over. So the effect would actually be that portion in the middle. Okay, so it's not at the observational point, it's actually at the point that we don't observe. That's the problem here. That's why we're having to do the difference. Now what happens is, if we can actually follow the control in terms of where they're at, so we have a pre-treatment measurement of the control and a post-measurement of the control. We have a pre-measurement of the control for the treatment and a post-measurement of the treatment. what we can do is we can take the difference between these two on their control. We can take the difference between the treated, pre and post. Then from that measure, we can then difference one more time. Mm-hmm.
Sorry, is the observed effect at point B or point A?
Oh, and this, remember I told you there was like an issue with how what I was trying to get it to graph. Really, B, that little measurement, should be where the hand disappeared. But it was. But for now, right now it's not as big of a deal. Just consider it the B. It can still be in your mind the right way. It would just be a little bit of an adjustment. But the point is that we can't view what that jump was in the middle, what the effect, what we would refer to as the true effects. We can only see the observational outcome later on. But if I had drawn it the proper way, you would actually see that effect is a little bit smaller than what we see in terms of this big line here. But the only way we can pick it out is actually to take the difference between the groups, each group, and then if you take the difference after you take the difference of the groups, the difference across time, let me rephrase that. By taking the difference between this one and this one, I'm taking the difference for that group, taking the difference across time for this portion, and then from this to this, creating a difference across time for that group, and then taking the difference between those two, mathematically would give me what this is. You can check me if you want to, but it's there. Okay?
It's the YCO minus the YC1.
Well, it's a little more complicated than that. I know it's hard to see visually. I was going to show exactly what it looks like. Okay, let me show you this first, and this might help out first, and I'll go back. So the way we kind of consider it is that if we were writing this and we think about it at 2 times, so I think about the treated and their post, the effect would be, think about it as filling in. So if this is 1, that's 1. This is 1, then that's 1. So that means the effect is beta naught, beta 1, beta 2, and beta 3. That is the effect, or the expectation given treatment and post. In terms of the expected value with treated as 1 and post equal to 0, 0, 1, 0. Okay? That would be beta naught, beta 1. Not treated, post, that would be beta naught, beta 2. Not treated, not post, and beta naught. Okay? So we have all the effects that we can see here, right? Now, the way we can see it is difference out for the treated. So if I subtract this from this, I get beta 2, beta 3. The difference for the control is beta 2. So that is the difference for the across time for each group. Then if I take the difference across group, so remember it was beta 2, beta 3, and beta 2. When I subtract those, I'm left with beta 3. That's what we refer to as the treatment effect. It's the interaction. Okay? And in that case, that's why, so we're differencing across within the group. Then once we have that, so that would be the sort of the difference across time. And then we difference across the groups. So that's why it's called the difference in difference. Now, I could do this the opposite way, too. I could difference across the groups first, and then difference across time. Same answer. Doesn't change. Okay? So this is exactly what the difference in difference is doing, and where it gets its name. So we can go a little bit deeper, too, because we can look at the beta 1. We can actually test if it's 0 or not. Now, most people only care about the interaction. They don't really care about the rest of them. But the other ones do give us information. So beta 1, if we can't say it's significantly different than 0, then basically there is no permanent differences between the treatment and the control. If we can't say that beta 2 is significantly different than 0, there's no common trend over the pre and post treatment. So just think about it this way. The difference in difference method differences permanent differences and common trends affecting both the treated and the controlled. So basically, the different groups are affected consistently over time is sort of what we're thinking about here. Okay? Just go back one. That's one way to think about it. The other way is to think about it in these terms, the way I was doing it on the graph. So here's a treated in the post period, treated in the pre-period, control in the post period, and control in the pre-period. What I'm doing is I'm taking the difference of the group. Well, actually, this is the difference in time over the group, difference in time over the group. Then this one is the differences between the treatment and the control group. Okay? That would make it, the effects is what we're looking for is the portion in the middle that we can't observe. And just keep this in mind that basically the control group identifies the time path of outcomes that would have happened in the absence of treatment. This little thing that we're trying to do, we're trying to create a counterfactual that says in the absence of treatment, this would have been the effect. So everything that we observe is due to the treatments. Okay? So there could be, but note that by me saying this, don't think just because there's a difference in levels that there's a problem. Level effects don't it doesn't affect us at all because we can control for that.
So like during that jump where there would be a break of that line of that treatment.
No, so this is the break. If I had drawn it properly, it would stop here and then go in still a parallel line. Because this is kind of, the reason I don't like this, or the way I drew it is not exactly right, because it looks like there's an upward trend here. That would mean that there's something different that I'm not controlling for. Really, if I'm doing a proper way of controlling for it, I should have saw the jump, and then the parallel line should have continued on, in their treatment. So sorry about that. It's just my drawing skills in R are not very well. Or I want to say that R wasn't listening to me because I kept telling it to change it and it just kept drawing the same thing. So I kind of gave up a little bit on that. But yeah, so just to get the idea that basically there's some parallel jump here that we can't, or there's some discrete jump, let me say it that way, which we attribute to the policy treatment that we have. And then that once we do that, what we're trying to do is we're trying to tease out the information. And one of the ways of doing that is first, you take the difference across time for the groups. Once you have that, then you difference the outcome across the two groups. That should be the, and we're doing that, but in some ways, that's exactly what oh, hold on, there's something missing here. Okay, another problem. Make sure you throw my beta 3 back in there. I forgot to put it in there, in my slides. Yeah, okay, it's there. So what that little thing I was describing is basically found, or that difference, and then the difference is found by that beta 3. Okay, that's exactly the intuition that we have for why that interaction is sometimes we refer to it as a true effect, or it's the effect that we can't see in between the two observational outcomes. Okay? There's a few assumptions that go along with this, and I think I've already mentioned those. And we could do a simulated example with this. It's not as important, I guess, but I guess it is sort of important to see what would happen if we just took an estimation and decided to do what we usually do. So we have a dummy variable that says, what the time event was. If we look at people we saw received the policy versus didn't receive the policy, and then some controls for household size, education, and urban. If we were to run this model, see, this would be what we assume the policy treatment is, right? And in this case, given the simulation, it would say that it's positive and quite large. If you want to think about it as dollars, I can't remember what I was thinking about in terms of the outcome, but I think it might have been in terms of wages, if I remember right. But once we actually start thinking about the difference in difference, we can actually take it one step further. Think about our post or our time dummy, our treatments, and our interaction. We could actually think about this as being possibly that we were underestimating the effect of our treatments. In this case, if this was true, I'm almost doing it by 50%, or actually a little over 50%. A little less than 50%. So that could be a big thing there. If I'm trying to sell the particular effects of this policy about the goals and everything, and I get the outcome, if I didn't take account of the differences across time and differences across groups, maybe it wouldn't have been, my policy wouldn't have continued because they didn't see the true effects of what it was actually causing. And that's the thing about it. So we're only getting one aspect by only doing just a dummy variable for that. In terms of actually, if we add in more controls, we might have still been underestimating. Okay, there are other characteristics we weren't considering, their education levels, where they were living at the time, their household sizes. We could have been even underestimating more. Okay, so that's why if we're going to do something that involves some type of policy and we can actually tease out exactly who was treated, who was not, we can control, there's no movement within, and we can actually, we know some information about the pre and the post, we can actually get better information on the outcomes of the policies. Okay? But this is just a simulation. This is only one of them that I do. Sometimes I have one I do for honors that shows that when you do it by not considering the differences across time and groups, that the effect is something like this, but once you do take into account those differences, the policy effect is 0. Okay, it doesn't mean that it's always going to move in one direction. It can actually be, it's very dependent on what you're actually looking at. Then there's also something called a triple diff and diff. Oh, sorry.
In a condition wherein you have your coefficients being, let's say, coefficients of other variables, you find them being 1,000 point something, and then the other one is 0.1. Is there a problem in that case, or is just normal based on based on the data that I gave to the problem?
I would need a lot more information. So there's always a reason why you're getting something out of that program, and it's always based on the properties of that data set. Now, if you're talking about something where you're getting something that's quite large, and then you add one variable, and all of a sudden everything goes to the way you're describing, I would think something's a little off in terms of structure or something. Actually, we'll do it in the break. That might be more helpful because I would need more information than just being big versus small. Yeah. So one of the problems with the diff and diff is that basically there's certain assumptions that we have to assume that whatever groups we have are comparable. That could be a bad assumption in some cases. So in that case, when we're using 2-period, 2-group models, sometimes we can break some of the assumptions that are standard within the diff and diff. And then we also have ways of adding in two-way fixed effects, are ways of some of the methods they use, but that can also create misleading or sometimes strange results as well. But there are new estimators besides these, and there's a lot of extensions to how we do the diff and diff. Okay, and one of those is a difference in difference model, to where, what if we threw a third group into there? One that was an additional, in this case, control. I'm not sure if I gave a specific example. Let me see. Oh, actually, I'm not. This is just about new research in diff and diff. I didn't actually put the triple diff in there. Okay, so there is a triple diff that is a way of doing this. It helps us create that we're no longer relying on this assumption of parallel trends, which is a possible way of doing this as well. Sorry, I thought I had put it in here. Okay, so like I said, don't go to just the basic ones. There are a lot of new innovations in this. And the last little part that I'm going to cover is to try to show an example of CRE and quantile models. Remember, I told you that basically there are methods for using or trying to control for unobserved heterogeneity in quantiles. But the research is quite large in terms of different directions people are taking. In that case, we can try to show a few of these, and that's what I'm going to do here, is basically we can offer, the CQR can offer additional information about the conditional distribution and the heterogeneous effects. At the same time, we can try to include individual specific effects in the CQR, but again, we're haunted by the IPP. But we have a few methods that we've developed to deal with this, which one is the penalized CQR. So we're basically introducing a penalty to that objective function. And that penalty is sort of helping us hopefully reduce or shrink what we refer to as the fixed effects, or sort of reducing the bias. So that's one version of this. The other is something called, I'm not sure if it's Kane or Kana, basically involves estimating a first stage OLS model and then borrowing the fixed effects from that model after they're calculated and including them, or sorry, with a little calculation and then including a statistic from that information in the quantile regression. Okay? And in some ways that would help us narrow down maybe the outcomes from the unobserved effects. In my opinion, when I've done this in the past, it hasn't gone very well. Some people have used it and it has gone well. But there is an overlying assumption here that you're holding the fixed effects or the unobserved effect constant across quantiles. You're saying everybody has the same effects. That's not probably a very good assumption. Okay? And there's also another one that called the smoothed. So basically I've said that the objective function is not smooth, and there's ways of adding that to, or trying to apply smoothness to the objective function. And then the one that I typically use in the work that I've done with this is basically using CREs. I just wanted to give you an idea of how it looks in terms of our regression from the wage pan and seeing how each of them are being estimated. As you can see, there is no real big pattern here, right? Each of them are doing their own little thing. This is why I said the research in this is varied. Now, there are some that kind of mimic pretty well what they're trying to do. So this is the purple one is the CRE, and the blue one is the traditional quantile pooled without trying to control for unobserved effects. In this case, you see that they're following each other, but the other ones, the lasso and the or penalized one, and the Kine are basically going in opposite directions. In other cases, we find that some of them are going the same direction, but you see that there's a lot of different outcomes happening here. And each of them are trying to do the same thing, using a different method, but without going into further detail, knowing which one's doing the right thing, we're not so sure. I could set it up to try to test which one, like a simulated data. But this one I was just trying to show you that each of those methods are going to give you something slightly different. And it basically is going to show you that those effects are changing over the system, but some are rising while some are falling. Okay, so just keep that in mind when you're using this method. There's no one tried and true method that's going to help you with using quantiles and unobserved effects. Okay, you have to test, you have to look at what your how your data looks, and what might be going on there, what properties you're dealing with. Okay. Okay, so that was the end of my slides for today. So we had that break from 2:30 to 3.